Hello friends, welcome to CEC Live Lectures. Dear friends, today in this session we are going to talk on band theory. We have already conducted one session on band theory, and according to the demand of this subject, today we are again going to have an elaborative session on band theory where we are going to discuss on semiconductors. And for the discussion on the topic, we have with us in our studios Dr. Sonia Bansal. Dr. Sonia Bansal is assistant professor and she is teaching in YMCA University. She is a prolific professor, and through the live platform of CC, she always believes the maximum to be communicated and disseminated to the students. So I would suggest that her lectures would be beneficial for you, so you should keep watching them through this live medium as well as through YouTube too. Now let's welcome our guest Dr. Sonia Bansal, and let's try to have a vivacious session once again. Hello ma'am, welcome to the lecture.
Thank you. Okay, dear students, last time we discussed about the band theory of solids, in which we discussed about the insulators, semiconductors and conductors, and then we realized that how the conductivity changes by the use of the electrons. This part we will discuss about the band theory of the solid part 2, in which we again start with the band theory of solid. What is this? In order to account for decreasing resistivity with increasing the temperature, it means when the temperature increases, the resistivity will decrease, as well as the other properties of the semiconductor will be changed, and that new theory known as the band theory, and it is introduced to define the solids and its characteristics. The essential features of the band theory is that it allows energy states for the electrons are nearly continuous over certain ranges, and that are called the energy bands, with the forbidden energy gaps between the bands. Means we discussed about the valence band and conduction band, and the difference between these two bands, we have the forbidden band, and that is known as the energy band gap. Now we discuss about here that the band theory of the solid, we consider the wave functions of the two hydrogen atoms far enough apart so that they do not interact with each other. Let us see here, this is the one hydrogen atom, this is the another hydrogen atom, and this is represented by psi. Psi is the wave function which represents the property of this wave, and Va, this is the velocity by which the electron by which the atom is moving, and this is the another atom by which the this is the Vb, velocity by which it is moving, and the phi b represent the characteristics of this atom. Then these two atoms do not interact with each other. Now here we see that the interaction of the wave functions occurs as the atom come closer to each other. Here we see that these two are closer to each other. Here we see that phi A plus phi B. This is the case of the symmetric. An atom in the symmetric state has a non-zero probability of being half wave between the two atoms. Here we see that here we are having the halfway between the two atoms, while an electron in the asymmetric, this side we define the asymmetric, where we see that one electron having the positive and one atom is a negative. Then in the case of antisymmetric, where we define the wave function phi A minus phi B to define the two atom system, while an electron in the antisymmetric state has a zero probability of being at that location. Now, we define that in the symmetric cases, the binding energy is slightly stronger, resulting in a lower energy state. Means the electrons are tightly bound at the lower state if we talk about the symmetric system. Thus, there is a splitting of all energy levels like 1s, 2s and so on. When the more atoms are added, as in the real solids, there are the further splitting of the energy levels. With the large number of the atoms, the levels are splitting into nearly continuous energy bands. Means we are having a large number of atoms, then we are having the different more levels which are splitted to each other, and they define the continuous energy bands, with each band consisting of number of closely spaced energy levels. all bands. Here we see that this is the one band, this is the another band, and these bands are splitted into different. This is the separation of electron, this is a one. Here we see that this is the allowed energy band. This is the graph between the energy versus the separation between atoms. Here we are having a lower state, this is the higher state. The difference between these define the allowed energy band, and this atom contains the 6 atoms. This we can represent by the band structure. Here we see this is the level destination of the atoms. One isolated atoms defined here. We are having a 1s, 2s and 2p. Here number of available electronic state. This is the 2 electron field 2 and 6. This is the split level where the two interacting atoms, then we have the two levels, 1, 2 here, at the second level we have 2 and here we have 2. This is the number of the available electronic states. Now you consider the 6 interacting atoms. Here we have 1, 2, 3, 4, 5, 6, and for the upper level also we have the 6, and final level we have 6 splitting levels to jump the electrons from lower state to the higher state. These are the number of electronic state we defined by the 12, 14 and 12 and 36. Now we define it when they are closely spaced, then we take it as a band. In case here we have n interacting atom, as the number of atoms will increase, the levels will increase, and when we are taking the n number of atoms, then we get the bands, because all the levels are equally spaced and they are having the very less distance between them. So here we define the levels by 2n, bands by 2n, 2n and 6n. These are the number of available electronic states and all the levels defined by the bands. We consider the sodium, example of the sodium atom. Here we see that sodium 3s1, only one occupied, so half full. Empty 3p, empty 3p. This state is empty 3p state overlaps with the half filled 3s state. Here we see in the blue, this is the filled state. There are the many empty state above it, and this 3p is the empty state, and it is overlapped with the 3s level. Now easy for the valence electrons to jump to the higher unfilled state by presence of a small electric field. Here up to blue we are having the filled state. There are the many empty state into which the electrons can be excited by a small electric field, because in this case the bands are overlapped to each other, so it will be easy for the electron to jump into the higher state, and the sodium will work as a conductor, and sodium is a good conductor. Now see, here we see this represent the forbidden, this represent the allowed empty, and this is the allowed occupied. Here we see in the conductor, this part is the filled and this is occupied by the electrons, and above it we are having the empty allowed state, and in between up to it we are having the again the forbidden band and then allowed state. In case of the insulator, the band gap is more between the valence band and the conduction band. Valence band is the filled, it is occupied and is also allowed, and the upper part which is empty, this is conduction band, and the band gap is more. In case of the conductor, it will overlap to each other. In case of semiconductor, we are having a very less or very small band gap between the valence band and the conduction band. The valence band occupied by the outermost electrons, and the conduction lowest band with the unoccupied state. The conductor valence band partially filled or half filled in the copper. The conduction band overlap the valence band. It is explaining the case of the conductor, and the example is the copper. Now we take here we see the comparison between these three, that resistivity versus the temperature. Here we see that in this diagram we see resistivity versus temperature graph, which represent the conductor. at the normal temperature, this conductor for the low temperature, and here semiconductor at the room temperature. Resistivity versus temperature for a typical conductor would define here a linear rise in the resistivity with the increase in the temperature at all but very low temperature. Here we see the resistivity versus temperature for a typical conductor for a low temperature. We see that the curve flattens and approaches to a non-zero resistance at T approaches to 0, and this case we can consider for the superconductors also, where the resistivity drops to 0 when the temperature will be low. In case of the semiconductor, we see that the resistivity at the 0 Kelvin will be high, and at the higher temperature resistivity will be low. Here we see in the diagram, this is a linear curve which represent that the resistivity increases dramatically at T approaches to 0, and as a T increases, resistivity will decrease. Now here one of the model which represent the band theory, which is the Kronig-Penney model. The Kronig-Penney model, here we see first the diagram. There here we are having the periodic arrangement of the lattice here, and Vx here we define the potential, and V0 we have defined the potential at the surface. And here Kronig-Penney assumed that an electron experiences an infinite one-dimensional array of finite well. Here we define the finite value of the potential well is V0. The height of the well is V0. Now each potential well models attraction to an atom in the lattice. So the size of the well must correspond roughly to the lattice spacing. Here this is the lattice spacing, and this represent the A. 0 to A represent the lattice size, and this is the lattice spacing. Now this is the Vx, we are defining the potential, and here we are defining the size of the lattice, and 0 to A is the width is the length of the well, and on the next side we are having a value of minus B, and for the next we are having a plus B. It means this size of the lattice is B. Now we define it as that an effective way to understand the energy gap in the semiconductor is to model the interaction between the electrons and the lattice atoms. Kronig and Penney developed a useful one-dimensional model of the electron-lattice interaction. Here we are having the electron is in the lattice, and that is the electron-lattice interaction. That's what defined by the Kronig-Penney. Then what is the behavior of electron in the potential well, or how it interact with the lattice? In 1931, Kronig-Penney defined this one-dimensional model of the electron lattice. Now here we see, since the electrons are not free, their energy are less than the height of V0. Here the electron is not free because electron is moving in this well, and the height of this well is V0. It means the potential of this well is V0, but the electron is essentially free in the gap 0 to X and A. It means the value of electron is free in this is 0 to A. The electron is free. This point is x-axis, and here the electron is free to move, where it has a wave function of the form by the psi A power e I k x plus b e power minus I k x, which represent the wave number, where k represent the wave number, x represent the direction of the electrons moving, and here A and B are the coefficients. In the region between the this region A and A plus B, the electron can tunnel through it, and the wave function loses its oscillatory solution and becomes exponential. That's why we define it as psi is equal to C e power kx plus d e power k minus kx. Now again we are having a next coefficients, different coefficient from the previous, which is C and T. K is again the propagation constant, that's value defined by the k square is equal to 2m v naught minus e by h cut square. This case we are defining for the electron position in the A and A plus B. Previously we defined the position of the electron in the lattice 0 to A. Now in the Kronig-Penney model, if we solve these two equations, then we have before we are defining along the x-axis. Now after the tunneling we have this equation. Now in this case, in the Kronig-Penney model, we have the solution of this equation. We have k square b by 2k sin ka plus cos ka is equal to cos ka. Here we see that the value of x is changed by the lattice value, which is a, because we are not considering for the full x-axis. We are taking a particular length of the well where the electron are moving, that is a. That's why we have in this equation the value is k square b 2k sin ka plus cos ka is equal to cos ka. Now the left hand side is the limit to values between the +1 and -1 for the k values, means this value we will define the propagation constant can go from the -1 to the +1 for to define the equation for the positions of the particle in a well. By plotting this, we observe that there exists restricted shaded forbidden zone for the solution. When we plot this k square b 2k sin ka plus cos ka, means we plot the graph between the left side versus ka, then we got the forbidden band. These are the forbidden band which defined by the blue, and these are the forbidden band, and in between that we are having the allowed state, means electron cannot move in this state but can move in this allowed state. Every allowed state having the forbidden band. Matching solution at the boundary, the Kronig-Penney finds that this equation, and where k is the another wave number, and this equation defines the allowed and forbidden band in the lattice. Now here is the diagram. Then this plot in the left side of the equation, ka for k square ba by 2 is equal to 3 by 2, and the allowed values must corresponding to the k for the value of k must be root of 2me divided by h square e. This plotted function lies between the, here we see that the value is lies between the +1 and the -1, because the value of cos ka in between the +1 and -1, and the forbidden value are shaded in the light blue. Here we see that these are the forbidden, and here we are having the allowed state. If we plot a graph between the energy versus ka propagation constant, then we see that the corresponding plot of the energy versus ka for k square ba divided by 2 is equal to 3 by 2, showing the forbidden zone gap. Here we see from 0 to pi we are having the allowed state, which is representing by the blue curve. After that we are having a break, that break defined the forbidden band. After that again we are having the allowed state between the pi to 2 pi, that is also the allowed state, and again after 2 pi we are having the forbidden. At 2 pi we are having the forbidden band, and then again we are having the allowed state, and in this way we are getting the allowed state, forbidden band, allowed state, forbidden band, and so on. What are the important differences between the Kronig-Penney model and the single potential well? The single potential well we have already discussed in the solid state physics when we defined the free electron theory. Then what are the difference between the Kronig-Penney? Kronig-Penney works on the periodic arrangement of the lattice, but in the single potential that was not defined the periodic potential. But here we define the difference between the Kronig-Penney model and the single potential well. For an infinite lattice and the allowed energies, here we considering the lattice is infinite and the energies are allowed within the each band are continuous rather than discrete, and in a real crystal the lattice is not infinite, but even if the chains and the thousands of the atom long, then the allowed energies are nearly continuous, because there we do not define by the bands, but not defined by the levels, but defined by the bands when the number of atoms will increase. In the case if we talk about the 3 dimensional crystal, it is appropriate through the wave vector k. It depends upon the wave vectors k. The wave values of the wave vectors can be changed, and the allowed ranges of the k constitute what are referred in the solid state that will be defined by the Boolean zones. In a real crystal, the potential function is more complicated than the Kronig-Penney squares. Thus, the energy gap by no means uniform in the size. The gap sizes may be changed by introduction of impurities or imperfection of the lattice. Here, what does I mean by the gap size? Means the forbidden band can be changed, or the value or the energy band gap between the conduction band and the valence band can be changed by, it may be increase or it may be decrease by introducing the some impurity or by doping the some material in the lattice. These facts concerning the energy gap are of the paramount importance in understanding the electronic behavior of semiconductor. It means when we define the theory of the semiconductor, the Kronig-Penney model plays a essential role. Now, band theory helps to band theory and the conductivity. How the band theory used in the conductivity, how we define the conductor insulated by using the band theory. The band theory helps us to understand the difference between the conductor, insulator and semiconductor. As a good conductor like copper can understand by using the free electrons. We are having a free electrons in case of the conductor. And in the semiconductor, the band gap is overlapped and the electron can jump from one state to the another state easily. And it is also possible to make a conductor using a material with its highest band filled, in which cases no electron in that band can be considered free. Means the valence band should be fully filled, and the conduction, it is easy to go into the conduction band. If this filled band overlaps with the next higher band, means conduction band and valence band are overlapped to each other, however, so that effectively there is no gap between these two bands, then by applying the electric field, the electrons from the filled level may jump to the higher level, and they are easy to conduct the electricity, or they are easy to get the higher conductivity. This allows conduction to take place, although typical with the slightly higher resistance than in the normal atom. Such materials are known as the semi-metals. The valence band and the conduction band, in case of the semiconductor, the band structure of the insulators and the semiconductors resemble each other quantitatively. Valence band and the conduction band. Normally, there exists in both the insulator and semiconductor a filled energy band, which is referred to as a valence band, separated from the next higher band, which is the conduction band, by an energy gap. Sometimes in the case of the conduction, it is overlap. In this gap, at least several electron volts, the material is an insulator. It is too difficult for an applied field to overcome that large energy gap. When we are talking about the insulator, the energy gap is too high, and we apply the high voltage current, still the electrons cannot jump from the lower state to the higher state. Or if we apply the thermal excitation, is also difficult to take the electrons from lower level to the higher level. And it is having the insufficient energy to conduct the electrons from lower band to the higher band, means valence band to the conduction band. The smaller energy gap creates the semiconductors. As we already discussed, that the energy gap smaller than about the 1 electron volt, then it is possible for enough electrons to excite it thermally into the conduction band, so that an applied electric field can produce a modest current, and this result a semiconductor. We are talking about a semiconductor. That semiconductor, that the energy band gap between the semiconductor is very less. The semiconductor are of two types. Number one is the intrinsic semiconductor and second is the extrinsic semiconductor. Intrinsic semiconductor, we talk about the pure semiconductors where no doping takes place in the semiconductor, and in case of the extrinsic semiconductor, we are having a two type of semiconductors. One is P type, means electron, and second is N type, means hole. P type for holes and N type for electrons. What is intrinsic semiconductor? In the intrinsic semiconductor, no impurities are added. It means they are the pure semiconductor materials. These semiconductors possesses poor conductivity, and the elemental compound semiconductors can be of the intrinsic type. The band gap in this semiconductor is very small. So even at the room temperature, some of the electrons from the valence band can jump to the conduction band by thermal energy. The jump of electron in the conduction band adds one conduction electron in the conduction band and creates a hole in the valence band when it shifts from the valence band to the conduction band. The process is called the generation of an electron hole pair. Means to jump the electron from valence band to the conduction band, we are having the generation of electron hole pairs. In the pure semiconductor, the number of electrons in the conduction band and the holes in the valence band are equal. But in the extrinsic semiconductor, these extrinsic semiconductors are called the impure semiconductors, formed from an intrinsic semiconductor by adding small quantity of impurity atoms, which is called the dopants. Means some atoms are doped into the pure semiconductor, and then we can get the extrinsic semiconductor. The process of adding impurities to the semiconductor crystal is known as the doping. This added impurity is very small, of the order of 1 atom per million atoms of the pure semiconductor. Depending upon the type of impurity added, the extrinsic semiconductor are classified into two types. One is P-type semiconductor and second is N-type semiconductor. Thank you.
With this one, thank you, ma'am. Thank you so very much for giving us this session on semiconductors. Friends, we are back after a short break and we are going to discuss more. You're requested to be with us. Thank you. Hello friends, welcome back to this session. Friends, you know that today we are talking on band theory, and in band theory we are specifically talking on semiconductors. Through our previous session we discovered a lot on semiconductors, and as per the promise, here we are again for you to discuss. Friends, for the discussion we have with us in our studios Dr. Sonia Bansal. Dr. Sonia Bansal is an eminent professor. Through her we always get knowledge on various topics and issues. So friends, we would like to welcome her once again and would request her to continue further. Hello ma'am, welcome back.
Thank you. Thank you. Welcome back students. We are talking about the semiconductors. Semiconductors means when the band gap between the conduction band and the valence band is very less, and electrons are easy to jump from the valence band to the conduction band by applying the small electric current. And we are defining these semiconductors by the two types. One is P type and one is the intrinsic semiconductor and second is the extrinsic semiconductors. Intrinsic means pure semiconductors and the extrinsic means impure semiconductors, where we are adding some impurities in it. And then this extrinsic semiconductor are again divided into two parts. One is the N-type semiconductor and another is the P-type semiconductors. We are discussing about P-type and N-type semiconductors. Now the application of the band theory to the N-type and the P-type semiconductor shows that extra levels have been added by the impurities. It means we are talking about the extrinsic semiconductor where we add the impurities to make it the P-type or N-type semiconductor. Here we see that the N-type valence band, this is the conduction band, and the difference between these two is known as the band gap. And here in the downside of the conduction band we are having the Fermi level, and this is the extra in electron energy levels up to which electrons are filled. Now here in the P-type we are having the conduction band and the Fermi level is in the P-type Fermi level is above the valence band. This is the extra hole energy levels and this is the extra energy and extra electron energy levels. If we talk about the N-type and the P-type, it is the Fermi level is near the valence band, and in the N-type the Fermi level is near the conduction band. In N-type material there are the electron energy levels near the top of the band gap so that they can be easily excited to the conduction band. In the N-type in the P-type material, extra holes in the band gap allowed excitation of the valence band electrons, leaving mobile holes in the valence band. Now here we see that the P-type semiconductor, the addition how we get the P-type semiconductor means how we get the impure semiconductor by doping the trivalent impurities such as boron, aluminum or gallium to any intrinsic semiconductor, which creates the deficiency of the valence electrons, which is called the hole. Here we see this is the acceptor impurity creates a hole. It is typically to use the B2S6 diborane gas to diffuse boron into the silicon material. This is the boron atom which is added as a impurity in the silicon semiconductor. Now here we see and we get the P-type semiconductor. In the N-type semiconductor, the addition of pentavalent. In the previously we add the trivalent, but for the N-type we use the pentavalent impurities such as antimony, arsenic or phosphorus contributes the free electrons, greatly increases the conductivity of the intrinsic semiconductor. Here we see in the diagram, again we are taking the intrinsic semiconductor silicon and we are adding the phosphorus into it, and then we diffuse the phosphine gas BH3 into the system, and we see that the antimony added as the impurity in case of the N-type semiconductor, and this is the donor impurity contributes for the free electrons. Now we get the P-type and N-type semiconductors. The two terminals. What are the, here we are defining the simple diodes, means p-n junction diode. We are having a p-type semiconductor attached with the n-type semiconductor, and then we get the simple diode. The two terminals called anode, which is towards the p side, and cathode towards the n side. At instant the two materials are joined. Electrons and holes near the junction cross over, combine with each other. Holes from the p side cross and to the n side, and free electrons cross from the n side to the p side. Means holes can move from p to n and electrons can move from n to p. At the p side junction, negative ions are formed, and at the n side of the junction, positive ions are formed. The n-type material and p-type materials become extremely useful when we joined these two with each other. Means when the p-type material and n-type material join together, we are having a p-n junction, and this create a diode. And the p region means here this side we are having the majority of charge carriers are holes, and the minority charge carriers are electrons. But here in the n region, the majority carriers are electrons and the minority carriers are holes. Before the p-n junction is formed, no net charge neutral. And here in the diagram we are seeing this represent the hole p region. This is the p-n junction which join the p-type and n-type semiconductor. This is the n region. Here we see that the majority are holes and the minorities are electron. Here we see that the majority are electrons in the n region and the holes are the minority, and this represent the randomly drifting free electrons. In the diode, here we are having a depletion region. Again we define here that this is the hole side and this is the electron side, means electrons are free to move here, holes are free to move, and in between that, which is the joining layer, is the p-n junction. At the instant the junction formation, free electrons in the n region near the p-n junction begin to diffuse across the junction and fall into the holes near the junction in the p region. For every electron that diffuses across the junction and combines with the hole, a positive charge is left in the n region and negative charge is created in the p region. Because electrons are diffused from the n region to the p region and the holes are diffused from the p region to the n region. That's why the positive charge left towards the n region and the negative charge left towards the p region, and they are forming a barrier potential. This region is known as a barrier potential, where we are having a positive and negative charge here, electrons. Now this is also known as the depletion region. This action continues until the voltage of this barrier repels further diffusion. The depletion layer, we see that when an n-type material is joined with the p-type material, how we get the depletion layer? When the E electrons diffused into the p region, in the p region they give up their energy and fall into the holes in the valence band covalent bonds. Since the n region have lost an electron, they have an overall positive charges. Now since the p region have gained an electron, they have an overall negative charges. The difference in the charges on the two sides of the junction is called the barrier potential, and it is of the range of millivolt. What is the barrier potential? The buildup of the negative charge on the P region of the junction and of the positive charge on the N region of the junction. Therefore, difference of the potential between the two sides of the junction is exist, and that's why it is the barrier potential. The focus between the positive charge form a field of forces which is called the electric field. This electric field is a barrier to the free electrons in the N region need energy to move to an E through the electric field. Means when we supply the electric field, then they will move. The potential difference of the electric field across the depletion region is the amount of the voltage required to move the electron through the electric field depends upon the type of semiconductor materials, amount of doping, temperature, and depend upon the temperature also. Means the potential difference between these two depletion region depend upon the material which we are using, what material we are doping, and what is the temperature in which the current is passed, and then we are getting the energy band gap. The diode energy diagram of the PN junction, here we see the in case of the diode what happened. This is the P region, this is the N region, this is the PN junction. In the P region, majority charge carriers are defined by the holes. This is the valence band, this is the conduction band. Similarly, in the N region, the minority carriers are holes and the majority carriers are the electrons. Now this is the case of the junction formation. Now at the equilibrium what happened, then a depletion layer is created, or the junction between these two N type and P type materials will be created, and this is the PN junction and depletion region where the combinations of hole and electron will take place. The every level of the N type valence and conduction band very less than the P type material. Difference in the atomic characteristics means pentavalent or the trivalent impurities which we are adding. After cross the junction, the electron lose energy and fall into the holes in the P region valence band. As the diffusion continues, the depletion region begins to form and the energy level of the N region conduction band decreases. Soon, no more electrons left in the N region conduction band with enough energy to cross the junction to the P region conduction band. Now, the figure B represents that the junction is at equilibrium state, the depletion region is completely diffused, has ceased. Now, it will be stopped and then create energy gradient, energy hill will be created. The electrons at the N region must climb to get the P region. The energy gap between the valence band and conduction band will remain the same. Now, what is the biasing of the diode? No electrons move through the PN junction at equilibrium state. Means if we talk about the equilibrium state, the electrons will not move through the PN junction. Bias is the potential applied. Biasing means when we apply the potential, if we are not applying any current in the depletion layer, electrons and holes will be in the P type and N type, and the no electrons will move in the PN junction. But when the biasing, when the potential applied DC voltage to the PN junction to obtain a desired mode of operation, means control the width of the depletion layer, two bias conditions will be get. One is the forward bias and second is the reverse bias. Now, the relationship between the width of the depletion layer and the junction current is defined by the depletion layer width is minimum, junction resistance will be minimum, then the junction current will be the maximum. If the depletion layer width is maximum and the junction resistance is maximum, the current will be minimum. It is opposite to each other. Depletion layer should be minimum to get the maximum current. Now this is a diode. Here we are seeing that the without passing the electric voltage, without passing the electric current or the voltage, no electrons will jump to the depletion layer. Here we see in the diagram, this is the diode connection which is connected with the voltage, and the voltage source or the bias connection are positive to the P material and negative to the N material. Here we see that this positive connected with the P and this negative connected to the N material. Bias must be greater than the barrier potential. If the barrier potential is the biasing we are applying, potential applying must be greater than the barrier potential. After that it will cross the barrier. Like we are taking the example of the germanium, it should be more than 0.3 volt for the germanium and more for 0.7 volt for the more than 0.7 volt for the silicon diode, and the depletion layer should be narrow, or limit of the current to prevent the damage of the diode. Here we see this is the forward bias because positive connect with the P side and negative connect with the N side. The flow of the majority carriers and the voltage across the depletion region. Here we see in the diagram this P side connected with the positive and negative connected with the N region. In diagram that the holes moving towards the depletion layer and the negative current from here, the electrons move towards the depletion layer. The negative side of the bias voltage push the free electrons in the N region of the PN junction. Also provides a continuous flow of electron through the external connection into the N region. Bias voltage imparts energy to the free electron to move to the P region. Here we see that they are moving towards the P region. Electrons in the P region lose energy. Positive side of the bias voltage source attracts the electron left the P region, and electrons will left the P region. Holes in the P region act as a medium or pathway for these electrons to move through the P region. Means electron jump from the negative region to the positive region, and these holes helps the electrons to move through the moves into the P region. This is the forward biasing. And effect of the forward bias on the depletion region, here we see at the equilibrium when no biasing takes place. Here the depletion layer, when the biasing of the electron takes place, we are taking the forward bias, narrows the depletion region and produce a voltage drop across the PN junction equal to the barrier potential. We see that depletion layer in the equilibrium state is more, but here when the biasing will takes place, or we are talking about the forward biasing, then the depletion layer is narrow. As the more electrons flow into the depletion region, the number of positive ions is reduced. As the more holes flow into the depletion region, on the other side, negative side, the number of negative ions is reduced. Reduction of the positive and negative ions causes the depletion region to narrow. Again we repeat that here we see that why we are having this depletion layer narrow in case of the biasing. Here this is the case of the equilibrium state where the depletion layer is, the width of depletion layer is more as compared to the width of the biasing in the biasing mode. We see that as the more electrons flow in the depletion region, the number of positive ion is reduced because the electrons are moving from N side to the P side, and here the holes will be reduced, and the more holes flows in the depletion region. On the other side, the number of negative ions is reduced, as we already talked about that. Here in this case we are having the negative ions here we are having the positive ion. If the electron will go this side, now this positive will reduce, now holes will come this side and this side will be reduced. In this manner, then the reduction of positive and negative ions takes place, and that causes the depletion layer narrow. The effect of the barrier potential during the forward bias. As the electric field between the positive and negative ions in the depletion layer creates the energy hill that prevents the electron from the diffusing at equilibrium state, that is the barrier potential. When apply the forward bias, free electrons provide enough energy to jump the hill and cross the depletion region. Electron got the same energy which is equal to the barrier potential to cross the depletion region, and then now the electron will cross the barrier potential. In addition of the small voltage drop across the P and N region due to the internal resistance of the material, which is called the dynamic resistance, which is very small and can be neglected. Biasing. Up to now we have discussed about the forward bias. Now we talk about the reverse bias. In the reverse bias, we are seeing here that the P type connected with the negative and the N type, N region or N material connected with the positive terminal of the potential, and this condition that prevents the current through the diode. Here we see the depletion layer is more as compared to the forward bias. The voltage across the voltage source or the bias connection are negative to the P material and positive for the N material. The current flows is negligible in the most of the cases, and the depletion layers will become widens. The short transitions time immediately after reverse bias voltage is applied. Here we see that in the diagram, the positive side of the bias pulls the free electrons in the N region away from the P-N junction. All the electrons move towards the positive side. Here all the holes moves the another side. Cause the addition of positive ions are created, widen the depletion layer. Means here the positive ions are easy to move in this region. In the P region, electron from the side, the voltage source enter as a valence electrons. The electrons move from hole to hole towards the depletion region, then creates the addition of negative ions. Here we see that the number of negative ions increases as the depletion layer widens. The availability of the majority carriers will be decreased. In the reverse biased, here we see that in the P region electrons are moving, here in the N region holes are moving. The electrons try to move from the P region to the N region, and it will move towards the positive ion. Extremely small current exists. After the transition, current dies out. Causes by the minority carriers in the N and the P region that are produced by thermally generated electron hole pairs. Small number of the free minority E in the P region. Here we see that a small number of the minority electrons in the P region are pushed towards the P-N junction by the negative biased voltage. This negative current will try to push the electron towards the P region, and the electron reach wide depletion region, and they fall down the energy hill combined with the majority holes in the n region as the valence electron flow towards the positive biased voltage, and which creates a small hole current. The conduction band in the P region is at higher energy level compared to the conduction band in the N region. An electron easily pass through the depletion layer. The depletion region is that region which are having the no free carriers. The further movement of electrons and hole across the junction stops due to the formation of this depletion layer. And the positive of the battery connected to the n-type material to the cathode, which is known as the cathode, and the negative of the battery connected to the p-type, which is called the anode. Here in the diagram we see that the negative connected with the p-type and positive connected with the n-type. And this form a diode. The electronic device which created by bringing together the p-type and n-type region within the same semiconductor lattice, which is used as a rectifiers and LED. Here in the n region electrons are free, and here in the p region holes are free to move, and the diode symbol is defined by this. This represents the diode symbol, where the arrow indicates the direction of positive current. This region defines the N, this is the P region. And in the reverse biased, the free electron in the N region are drawn towards the positive of the battery, and holes in the P regions are drawn towards the negative of the battery. Again, the depletion region will widen, barrier increases for the flow of the majority carriers. The majority charge carriers flow reduces to 0. The minority carriers generated thermally can cross the junction, which result the reverse saturation current, that is defined by the IS. This IS in the macro or nano amperes or less than that. The IS does not increase significantly with the increase in the reverse biased voltage. And in the forward, again we see that is positive connected with the p type and connected with the n type. And in the forward biased, electrons in the n type are forced to recombine with the positive ions near the boundary, and similar holes in the p type are forced to combine with the negative ions. Depletion region width reduces, and depletion width more in the forward reverse, but here it is reduces. An electron in the region sees a reduced barrier at the junction and the strong attraction for the positive potential. A forward bias is increased, depletion layer narrows down and finally disappears, leads to the exponential rise in the current. And the current in the forward bias measured by the milliampere. Thank you.
With this note, thank you, ma'am. Thank you so very much for giving us this session on band theory, where we discussed more and more on semiconductors. Friends, today we are taking your leave with the promise that we would be meeting again soon and would be discussing more on solid state physics. Till then, take care. Goodbye. Thank you. Thank you once again.